So Ivan, I would start. What do you say?
Perfect.
Okay, so welcome everybody to this fifth lecture on neutrinos. Today is the day of the tutoring lecture. We have the pleasure to have with us Ivan Esteban from the Ohio State University, who is giving us these lectures. And please remember that at the end of this class, there will be the virtual visit to the Carl Frank laboratory. So let's go with the classes. So here you go.
Okay, thank you. Thank you
Yeah.
for the introduction. Let me see if I can share my screen. Can you see it?
Yeah, we can.
Perfect. Okay, so well, good morning, everybody. In this 1 hour or so of tutorial, I'll try to cover some of the exercises that were proposed in the lectures by Pilar. And I think that the main goal of this tutorial will be to get some overall view of several topics more in depth than what is possible at some lectures, because we are going to try to do some actual computations. But first of all, let me remember that if you have any doubt, any question, anything that you want to share, please feel absolutely free to do it. This will make the tutorial more interactive. We will all learn more, because probably if you have a question, then 60 or 70% of the audience also has that question, and will make everything more interactive. Okay, so let me begin. The first problem that I wanted to tackle is one of the questions that was raised in the first lecture by Pilar. There she mentioned that generically for neutrinos, one can write, or for fermions, one can write two types of mass terms: the standard Dirac mass term that we all learn about when we learn quantum field theory, but one can also write a Majorana mass term that has this form. And the question is this strangely looking Lagrangian term a proper mass term? So is it Lorentz invariant? Does it generate massive particles? And more importantly, what about chiralities? How are different chiralities coupled in this sort of mass term? And to answer these questions and to understand how this operator generates masses, we will do a first detour, a small detour that I think that will make everything more clear. So let me start with a first question, just to warm up everything, that in principle has little to do with the original question, but we'll see that it's quite related. So imagine that we have a complex scalar field, a standard Klein-Gordon field, phi. Now the question is, if we have this field, how do we impose that particles and antiparticles are described by the same field? How do we impose that the particles described by this field are their own antiparticles? There are no different particles and antiparticles. There's one single type of particle. I will give you a couple of seconds to think about it, and if you have any comment, write in the chat. Otherwise, I'll answer the question myself. So if we have a generic complex scalar field, the way we impose
Ivan?
Yep.
There's a try.
Okay.
So the condition is phi equal to phi complex conjugate, yes.
Perfect. You read my mind. We just impose that the scalar field is real. So a complex scalar field describes particles and antiparticles. A real scalar field just describes one sort of particle. And for scalar fields, it seems very simple. We just impose that the field is its own complex conjugate. So the idea here, and the idea that Majorana had, is let's try and do the same thing for fermions. So the idea is that we will start with a standard Dirac field, and we will require it to be its own charge conjugate. And this will give us fermions that are their own antiparticles. Now, for fermions, it is not as simple as for scalars, because for scalars, the charge conjugation, that is the operation that takes a particle and converts it into its antiparticle, is just the complex conjugate. But for fermions, it is slightly more involved, because fermions are described by spinors, which are 4-component vectors. So what we will do, what Majorana did originally, is we start with the standard Lagrangian for a fermion that we all learned in quantum field theory courses, and we will impose that the fermion field is its own charged conjugate. And for the fermion field, the charge conjugate is not just the complex conjugate, but we also have a matrix here that is the charge conjugation matrix times gamma 0 multiplying the field. So once again, for fermions, the condition of being its own antiparticle is not that the field is its conjugate, but we also have to put here a matrix in Dirac space. And in principle, this should describe fermions that are their own antiparticle. So if we start from this Lagrangian, and among the solutions we impose the condition that we only keep the solutions that are their own charge conjugate, this in principle will describe fermions that are their own antiparticle. We already know that these fermions will have a mass m, because this is the standard Lagrangian for a fermion that we learn when we learn quantum field theory. And so the next question that we have to ask ourselves is this condition Lorentz invariant? That is, if one Lorentz observer imposes that he or she only wants to work with solutions that are their own charge conjugate, will other Lorentz observers also agree that these solutions are their own charge conjugate? In any relativistic quantum field theory, this is a condition that must be fulfilled, because otherwise different observers will disagree on whether particles are equal to antiparticles or not. So we will go and check that this condition, that the field is its own charge conjugate, is a Lorentz invariant condition. Let me say that for scalars, this was something very easy to check, or even trivial, even though I hate that word, because scalar fields do not transform under Lorentz transformations, and therefore this condition is automatically Lorentz invariant. But for fermions, we have to go and check it. How do we do it? Well, let me see if this works. The way to prove it is in principle relatively easy. And the Lorentz transformation is in black. Okay, so a Lorentz transformation is described by a coordinate transformation where my coordinates get transformed to some primed coordinates, which are just a linear transformation of the original coordinates. And for those of you that are more familiar with general relativity and space-time algebra and all these things, basically Lorentz transformations are linear transformations where this matrix has a determinant 1. So this matrix omega mu nu fully characterizes my Lorentz transformation, and under this Lorentz transformation, fermion fields also change. So my original fermion field is transformed to my new fermion field, psi prime of x prime, that is given by the exponential of I minus, I over 4 omega mu nu S mu nu. And here I have my original field. 4. Sorry about my handwriting. I have all these notes properly handwritten and scanned that I will upload to the web afterwards. So my fermion field transforms in this way, where this omega mu nu are the parameters that parameterize my Lorentz transformation, and this S mu nu are matrices in Dirac space. So basically, S mu nu is given by I halves times the commutator of two gamma matrices. So this is how my fermion field transforms under Lorentz transformation. So how do we check that this condition is Lorentz invariant? Well, it's quite simple. We assume so that psi is equal to its charge conjugate, and we want to check if the Lorentz transform field is also equal to its charge conjugate. That is, assuming that the field is its own charge conjugate in one Lorentz frame, is it also its charge conjugate in a different Lorentz frame? Well, to check it in principle, we just have to substitute here psi prime by this expression, assume that this holds, and check if this would be the case. So let's do it. This is a nice exercise on how to operate with the charge conjugation matrix and how all this algebra works out. Basically, the charge conjugate of psi prime will be by definition of charge conjugate the C matrix times gamma 0 times C prime complex conjugate. And if I apply this equation that relates psi prime to the original field in the other Lorentz frame psi, we just get C gamma 0 times the exponential of I fourths. So here the minus I goes into a plus I because of this charge conjugate, because of this complex conjugate. Omega mu nu, the omega parameters are real because remember that they come from a space-time transformation, and space-time coordinates are hopefully real. Then we also get here an S mu nu complex conjugate, and everything is multiplied by this field complex conjugate as well. Okay, so this expression gives me the charge conjugate of the Lorentz transform field. So we want to check that this is equal to the Lorentz transform field. And for this, we have to assume that the field is its own self-conjugate. So if the field is its own self-conjugate, then from this expression, we get, just by writing the charge conjugate of a field, we get that the psi complex conjugate is gamma 0 C to the minus 1 times psi. So this condition is equivalent to requiring the original field to be self-conjugate. So if we just insert this in here, we get that psi prime charge conjugate is C times gamma 0 times the exponential of I over 4 omega mu nu S mu nu star times gamma 0 c to the minus 1 and the original field. Okay, so now we have this horrible expression here that we want to somehow simplify to see if, once again, if the complex, if the charge conjugate of the Lorentz transform field is the Lorentz transform field itself. And to simplify this expression, we have to use several properties of both the gamma matrices as well as of the charge conjugation matrix. And I have conveniently put them in here. These are just algebraic properties that if you have the time and if you like matrix algebra, you can check by yourselves. And in particular, the most important property is this property down here, that the charge conjugation matrix times gamma 0 times 2 gamma matrices with the complex conjugate times this other matrix is just the original gamma matrices without any complex conjugate. So this tells us that if I take C gamma 0 S mu nu star gamma 0 c to the minus 1, this will be minus S mu nu. Why so? Well, S mu nu, if you remember from up here, is nothing but I times the commutator of two gamma matrices. So gamma nu minus gamma nu gamma mu. When I take the complex conjugate, S mu nu will be I times gamma mu minus the opposite. So because of this property here, when my charge conjugation matrices hit the gamma mu in the S matrix, they will just take the complex conjugate. So because of this, S mu nu complex conjugate just goes into S mu nu. Okay, so once again, because of this property, and since S mu nu is just the commutator of two gamma matrices, we get this other property, and we also get a minus sign in front of here because of this I here. So this complex conjugate means that we have to change the I with a minus I. This gives us this minus here, and also the two complex conjugates of the gamma matrices go away when we sandwich them in between these charge conjugation matrices. So far so good. Now this property implies that C gamma 0 is mu nu charge complex conjugate squared. This is 2 gamma 0 c to the minus 1 is the square of this. Here I just take the equation above and take take the square of it. Remember that gamma 0 squared is the identity. And this will give me minus S mu nu squared. And in general, if here I put a factor of n instead of a squared, I will get a factor of n here as well. And so when I take this exponential here and do a Taylor expansion, what I will get is that C gamma 0 times the exponential of I over 4 omega mu nu S mu nu complex conjugate times gamma 0 c to the minus 1 is nothing but e to the minus I over 4 omega mu nu S mu nu. So we get a minus sign here from this minus sign here, and also the complex conjugate goes away, because basically, and this is the important algebraic message that you should get out of this exercise, the charge conjugation matrix, when applied to gamma matrices, typically takes the complex conjugate of these gamma matrices because of this property. So this is basically the idea of why this matrix represents charge conjugation in Dirac space, because intuitively charge conjugation amounts to taking the complex conjugate. And so this C, the idea is that this C is the responsible for taking the complex conjugate of the gamma matrices. Okay, so once this is clear, we just take what we have learned, take this, we put it here, and we get that psi prime complex conjugate is nothing but the exponential of minus I over 4 omega mu nu S mu nu times psi. And if you go to our definition of how Dirac spinors transform and the Lorentz transformation, you will see that this is nothing but psi prime. So what we have seen is that if in one Lorentz frame we impose that the fermion is its own charge conjugate, then in all Lorentz frames, the fermion will be its own charge conjugate. That is, we have seen that this condition makes sense in a Lorentz invariant theory. Okay, so we know that we can take the standard fermion Lagrangian and impose the solutions to be self-conjugate in a consistent way. And so this will describe fermions that are their own charge conjugate. So far, so good. If there is any question or any doubt, this is a good point to ask. If no, I will move forward and I will tackle the original question. We now have to check that this Lagrangian here, that in principle has a weird form, actually generates Majorana fermions. That is Lagrangian here generates fermions with the standard fermion Lagrangian that are their own charge conjugates. And at the same time, we will also check that this Lagrangian here does not couple different chiralities. So this part will be less algebraic heavy than the other exercise. The basic idea here is that we will take this fermion field psi and we'll separate it into its left-handed chiral and right-handed chiral parts. So I will need, here we are. So we will take the field psi and separate it as a left-handed projector times psi left plus a right-handed projector times psi right. Here I am putting some properties of the left-handed and right-handed projectors that basically are 1 plus minus gamma 5 over 2. They are projectors, so the squared equals themselves, and they are orthogonal projectors, so their product is 0. And also remember that the gamma 5 is a matrix that anti-commutes with all the gamma matrices. Now, the important part here, and I will put this in a smaller window to emphasize it, the important part here is to understand what the charge conjugation matrix does to the left-handed and the right-handed projectors. So if we take the charge conjugation matrix and multiply it with the left-handed projector, this is, by the definition of the charge conjugation matrix, a factor of I times gamma 2 gamma 0 times the left-handed projector, which, since the gamma 5 matrix anti-commutes with all the gammas, when we pass this gamma 0, the plus will turn into a minus, because the gamma 5 matrix anti-commutes with all the gammas. And so this will be nothing but I gamma 2 right gamma 0. And when we pass this once again to the left, since gamma 5 anticommutes with all the gammas, we will get a factor of L here. Gamma 2 gamma 0, so we got here L times C. This means that the charge conjugation matrix commutes with the chiral projectors. And in the same way, one can easily prove that this is also the case. So the charge conjugation matrix commutes with the chiral projectors. We can first take the left-handed part and then multiply by the charge conjugation matrix, or do the opposite. It doesn't matter. So this means that when we take this Lagrangian over here and separate the psi field into the left-handed and the right-handed part, we will get something that looks like, also we get a factor of 1/2 times m times psi left transpose with the left plus psi right transpose with the right. Here I just took the transpose of this. And the left-handed and right-handed projectors are their own transpose, simply because the gamma 5 matrix is symmetric. Here we put a charge conjugation matrix, and we have to put a factor of L psi left plus R psi right. And the second term in this Majorana-Lagrangian is just the Hermitian conjugate of the first one. So to save time, we will write here the Hermitian conjugate, and that's it. Okay, so in this term here, when we expand the products, we will have 4 different terms. We will have psi left, psi left, psi left, psi right, psi left, sorry, psi right, psi left, and psi right, psi right. Now, because the charge conjugation matrix commutes with the projectors, the cross terms, that is the terms like with psi left, psi right, will have a term L C right that is equal to L right C that is equal to 0, because the left-handed projector and the right-handed projector are orthogonal projectors. And therefore, when we expand this product, we will not have terms with different chiralities. So this term only couples the same chiralities among themselves. And so minus the Lagrangian will be 1/2 of m psi left transpose C psi left plus psi right transpose C psi right. And if you go to the definition of the charge conjugate field of a fermion field, this is nothing but plus the Hermitian conjugate here, sorry. This is nothing but 1/2 psi left bar psi left. I will put here the Hermitian conjugate explicitly. Plus the same thing with left and right exchanged. So what we see here is that this Lagrangian only couples the chiralities among themselves. It does not couple the left-handed chirality with the right-handed chirality. And this will be very useful in the standard model, because in the standard model for neutrinos, we only have the left-handed chiral field to begin with. So in principle, we can write this sort of mass term. We still have to prove that this is a mass term, by the way, but we'll do so in a second. There's a factor of m here. With this sort of mass term, with one single chirality, we can generate a mass term. We don't need the right-handed chiral part, which we would for a standard Dirac mass term. Now, the key point here is that I can define two different fields, two new fields, psi1 as psi left plus its charge conjugate. So this is the definition. And I can define a second field, psi2, as psi right plus its charge conjugate. And in terms of psi1 and psi2, this Lagrangian here so this Lagrangian here is nothing but minus m halves psi1 bar psi1 plus psi2 bar psi2. Okay, so let us pause for a second and think about what we obtained here. So we started with this weird looking Lagrangian that involves the charge conjugation matrix, involves transposes of the fermion spinors and so on. And we ended up with two new fields that, okay, I have it here in a more clean way. So we started with this weird Lagrangian, and we ended up with two fields, psi1 and psi2. Psi1 only involves the left-handed part of psi, and psi2 only involves the right-handed part of psi. These two fields are their own charge conjugates, which is explicit from this definition. And furthermore, they satisfy, they have this sort of Lagrangian, which is a standard fermion mass Lagrangian. So this means that we started from this complicated Lagrangian, but if we rewrite it in terms of these two self-conjugate fields, we get a standard mass term for these two fields. So this means that these two fields will describe fermions with mass m, and at the same time, they will be their own charge conjugates. So if we do this for neutrinos, so if you take the neutrino field in the standard model and write this sort of Majorana mass term, you will end up with a neutrino field, with a massive neutrino field that will be nu L plus nu L charge conjugate that will have a mass, and furthermore, it will be its own charge conjugate. And here we did not have to mix different chiralities. So we did not have to introduce a right-handed neutrino. With a left-handed field, it's more than enough. So the take-home messages from this exercise are these two. First, that a Majorana fermion is nothing but a standard fermion with the condition of it being its own charge conjugate. And the second take-home message, if we start with one single chiral field and we add a Majorana mass term, we end up with a Majorana fermion. With a Majorana fermion for a field that is this particular combination of the chiral field we started with and its charge conjugate. Okay, so I will wait 5 or 10 seconds to see if there's any question or any
Yes.
comment or, yep.
Yes, you actually there is a question as it is pretty long. I will write it in the chat of everybody. So can read.
Let me see how
she left. Okay, you can read it directly. Is
if we take the conjugate with CR, neutrino is represented by C left. CCR. Okay. And suppose we have psi left. Okay. If we take the charge conjugate, we get psi CR. I don't really understand this part. So the charge conjugate of a left-handed field the charge conjugate of this is just psi LC. So this is just I gamma 2 gamma 0 times gamma 0 psi left star. We didn't have to talk at any point about psi right. We don't need the right-handed part to take the charge conjugate. And then what is true is that this so what neutrino is represented as anti-right-handed. So what is true is that one can check, well, basically, since this is non-zero, one can check that this is a right-handed chiral field. So this has a right-handed chirality, and this is why we can take this product, which only mixes different chiralities.
Let me just add a comment.
I don't know if this answers the question or...
I think so, because it's a problem of how the question is constructed. But let me say something more.
Yeah, yes,
we discussed about neutrinos, but don't forget that quarks also transform under weak interactions, and the C no conservation is also in the quark case, not only in the neutrino case.
Yeah.
Just to make clear that it is not the fact that we are speaking about Majorana nature that is making the weak interaction not conserving charge conjugation.
And also one point, so the fact that the weak interaction does not conserve charge conjugation does not mean that, so for instance, the charge conjugates of electrons, which are positrons, they take part in weak interactions. So this is a different story, and it's also what Lucas said, that the C invariance affects also works.
So there are no other questions about it, so you can go ahead.
Okay, perfect. If I didn't answer the question properly, just drop me an email and we can chat about it. So in the standard model, we have just one chiral field, nu left, and this all this we learned translated into neutrinos means that for neutrinos we can have either a Dirac mass term, which will require introducing a right-handed neutrino and will mean that the propagating massive field will be this combination, nu left plus nu right, or we can have a Majorana mass term, which will mean that the propagating massive field will be this other different combination. So then one possible question here is, well, why don't we just do the experiments with neutrinos, with propagating neutrinos, And since the propagation states are different for the Dirac and Majorana case, in principle, it should be relatively straightforward to distinguish between Dirac and Majorana. Why is it so hard? Well, there are many answers to this question, but one that I particularly like is that the standard model is chiral. So this means that the neutrino states we produced are the chiral left-handed projections of the neutrino propagating states, essentially. So when you produce a massive neutrino state, you are generically only producing the left-handed chiral part. And as you can see from here, for Dirac and Majorana, the left-handed chiral part is the same. Now, to distinguish between Dirac and Majorana, intuitively, I mean, this is a very hand-wavy argument, so don't take it as something extremely rigorous and so on, but the basic idea is that to distinguish between Dirac and Majorana, we need some sort of chirality flip somehow to really see the right-handed chiral part that is the one that distinguishes Dirac and Majorana neutrinos. And these sort of chirality flips are always suppressed by the neutrino mass. So this is one intuitive reason on why it's so hard to distinguish Dirac and Majorana neutrinos, and it's also one intuitive reason on why for massless neutrinos there is actually no difference between Dirac and Majorana, because in the standard model you only care about the left-handed chiral part, which is the same for both states. Okay, so I will leave once again 5 or 10 seconds for questions.
There are no questions.
Okay, perfect. So this already tells us why neutrino oscillations are not sensitive to the Majorana nature of neutrinos, because in neutrino oscillations we do not have chirality flips generically. So in neutrino oscillations we see neutrino masses because of a kinematic effect. We see neutrino masses because the vacuum energy of our neutrino states is different for each of the different mass eigenstates. And this kinematic effect generates all the interferences, and this is why we see neutrino oscillations. But in neutrino oscillations, we do not have generically chirality flips, and this is why neutrino oscillations cannot distinguish between Dirac and Majorana. And one can check, and indeed I will put it in the when I upload the solutions to the exercises, one can explicitly check that some phases in the leptonic missing matrix that are only there if neutrinos are Majorana, typically, that are typically there with neutrinos and Majorana, these phases never enter neutrino oscillations. So one can check it mathematically by writing the neutrino oscillation probability and checking that these phases go away, or one can check it by this intuitive argument that there is no chirality flip that would distinguish Dirac and Majorana neutrinos. Okay, and moving on to a more experimental part about neutrino oscillations, I would like to discuss one question that was raised in the theory lectures by Pilar, and that I think is quite interesting because it always pops up. And the question in principle does not seem, so it seems quite naive, and it's why don't charged leptons oscillate? So in principle, if we observe neutrino oscillations, why don't we observe charged lepton oscillations? So why don't we observe muons becoming into electrons after traveling for long distances? So any idea for this? So imagine that I prepare a muon beam. Why doesn't it transform into electrons after traveling for a long distance if muon neutrinos transform into electron neutrinos? Okay, so the first tip to help into thinking about this problem is what are neutrino oscillations? And in particular, what induces neutrino oscillations? Okay, so in neutrino oscillations, what happens is that when we generate a neutrino with some given flavor, this neutrino flavor eigenstate that I will call nu alpha. Yes, well, is generically a superposition of different mass eigenstates.
Yeah, even someone gave it wrong. We define flavor of charged leptons by its mass. So mass in this
That
case does not oscillate.
That is exactly the point. That is exactly the point. So neutrinos, neutrino flavor states are defined in the following way. An electron neutrino is the neutrino produced together with an electron. A muon neutrino is a neutrino produced together with a muon, and so on and so forth. And this is a combination of mass eigenstates. The mass eigenstates evolve differently, and this is why we have interferences, and this is why flavor eigenstates can transform into one another. However, for charged leptons, the difference between an electron, a muon, and a tau, it's nothing but its mass. So the way we distinguish an electron from a muon from a tau is by their masses. And therefore, by definition of what a charged lepton is, they are mass eigenstates. So mass eigenstates, so if we produce a charged lepton, for instance, a muon, this will have a well-defined mass. So it will not be a superposition of mass eigenstates that evolve differently and that interfere and so on and so forth. And so since we distinguish the charged leptons among each other by their mass, by definition, they are mass eigenstates. And so they are not superposition of states that evolve differently, because mass eigenstates are eigenstates of the Hamiltonian, and so they do not mix. And this is the main. This is the reason why charged leptons do not oscillate, because when you define a charged lepton, you define it as a mass eigenstate, and these are propagation eigenstates, so they do not change in propagation. Okay, and once this is clear, so now you already know why charged leptons do not oscillate. So every few months there's a paper in the archive saying that charged leptons should oscillate, and apparently nobody has realized it. So now you already know why these papers are wrong. And I will move on to a more experimental part. And in particular, we will try to estimate the number of, we'll try to estimate how we should build a detector in order to observe neutrino oscillations. Imagine that we are experimentalists and we want to observe neutrino oscillations because they are our first piece of evidence of physics beyond the standard model, and so this is quite relevant. And we want to understand how large the detector must be and where we have to place it in order to observe a few events per day. Okay, so for this, we will do a simple calculation, an order of magnitude calculation that is very relevant when one is designing experiments. Let me start with the second part. How far do we have to place a detector to be sensitive to this square mass splitting, which is of the order 10⁻³ electron volts squared? Well, we know that the oscillation probabilities go as the sine squared of delta m squared L over 4E. And so we want this factor to be of order 1. If our distance is very small, if L is very small, then this factor will be essentially 0 and we will see no effect. And if this L is very large, we will not be able to resolve the oscillations, and so we will not see this sinusoidal dependence, or that is really the smoking gun of neutrino oscillations. And so if we want this to be order 1, we have to put this in more reasonable units, and Pilar already did the work for us in the theory lectures. This is the sine squared of a factor 1.27 times delta m squared in electron volts squared times L in kilometers divided by the energy in GeVs. So we know that this is of order 10 to the minus 3, this factor here. Now the question is, what is the typical energy of neutrinos in a reactor? Well, in reactor, neutrinos are produced through nuclear interactions, through all the nuclear fission processes that take place that we use to generate energy in nuclear power plants. Now, what is the typical energy of a nuclear reaction? This is a question that I raised to you, so please feel free to answer it in the chat. What is the typical energy that is produced in a nuclear reaction? Is it GeV, MEV, KeV, TeV? Okay. Yep.
Mega electron volt.
Exactly. The typical energy in nuclear reactions, that is the typical binding energy in a nucleus, that is of order MEV. So the energy will be of order MEV, which is of order 10 to the minus 3 electron volts. GeV, sorry. Okay, my tablet stopped working, so sorry for the handwriting. This is a minus. Okay, so this means that down here we will have a factor of 10 to the minus 3. And since we also have a factor of 10 to the minus 3 up here, then these factors cancel each other. And this tells us that the distance to which we have to put our detector is of the order of a kilometer. So we have to take a neutrino detector and put it 1 kilometer away from the reactor to be able to observe neutrino oscillations. Now, the next question is, how large must this detector be? And this will be the last problem that I do so that you have time to go to Canfranc. So the number of events that we will observe in this experiment can be estimated as the flux. Now we have to divide, this is the number of neutrinos we produce per second. We have to divide this over all the, so we have so this is the flux that you produce at the reactor itself. If we are far away from the reactor, all the neutrino flux will be diluted as with a factor of the distance squared, just because all the neutrinos will be distributed into some sphere with radius L, with L where L is the distance at which we are. So this is the flux over 4 pi L squared. This is multiplied by the cross section of neutrino matter interaction. So flux times cross sections times the number of targets in your detector gives you a number of events. And so this is neutrinos per second per square centimeter. When we multiply by the cross section times the number of targets will be just neutrinos per second. And we have to multiply this by the observing time, by the time that you are observing. So this will give us just neutrinos, and this must be of order 10 neutrinos per day. So basically, we take delta t to be of order 1 day. 1 day is basically 20 hours. 1 hour is basically 3,000 seconds. So this is basically 1 day, which is 10 to the 5 seconds. The cross section is given with the typical cross section between neutrinos and matter is 10 to the minus 44 square centimeters. This phi over 4 pi L squared will be the flux, which is 10 to the 20 seconds to the minus 1, divided by 4 pi. 4 pi for a physicist is 10. So this is factor of 10 times the distance that we said it was of order of 1 kilometer. So this is 10 to the 5 centimeters squared. And the last factor is the number of target nuclei. So in your detector. So the basic idea here is that this cross-section is the cross-section between one neutrino and one nucleon in the detector. But our detector has many nucleons, and this is why the cross-section between one neutrino and the entire detector has to be multiplied by the number of nucleons in our detector. So how do we estimate this? Well, oops. This is simply the mass of the detector divided by the mass of a proton. What is the mass of the detector in kilograms? Divided by the mass of a proton. Does anybody know the mass of a proton in kilograms by heart? I don't. And there's a trick to know this, and the trick that I always use is that we know that in 1 mole of protons, so in 1 mole of protons, we have 1 gram of protons. So if we take an Avogadro number of protons, this is 1 gram. So the mass of 1 proton is 1 gram, that is 10 to the minus 3 kilograms, divided by the Avogadro number, which is 10 to the 24, more or less. And this is a simple way of estimating the mass of a proton in kilograms. Now, if we put all these factors, we know everything here except for this mass. You can do the computation, it's very simple. And we get that the mass of our detector must be of order 10 to the 3 kilograms. So we have to put a 1-ton detector 1 kilometer away from the reactor to observe neutrino oscillations. By the way, I don't have time to discuss it in detail, but there is a very nice Linux program called Units that does all these nasty unit conversions for you. It even has some constants inside, and it even has a mode in which it works with natural units, with h bar equals c equals 1. So you can convert centimeters to electron volts without any problem with this program. It's for Linux, but I think that there are also versions for Mac. So in any case, the summary is that to observe these neutrino oscillations, we have to put a 1-ton detector 1 kilometer away from the reactor. And let me finish this tutorial by introducing you the Daya neutrino experiment. So this is located in China, in the Daya nuclear complex. So this is an aerial view of the complex. These tiny circles here, I don't know if you can see them, these are the nuclear reactors. And this scale is 200 meters. So 1 kilometer is more or less here. So in the Daya experiment, here underground, they have these 1-ton detectors that are used to observe neutrino oscillations. So you need a 1-ton detector, which is more or less this size, 1 kilometer away from the reactor, which is more or less here, to be able to observe neutrino oscillations. And the Daya experiment has been a quite successful experiment to very accurately measure the square mass splitting, the delta M square 32, and its associated mixing angle. And the reason for this is that reactors produce many neutrinos. We just made the order of magnitude estimation, and you observe basically of order 10 neutrino events per day. So if you observe for 1 year, you can imagine that you get thousands of events, and with this, and with very good experimentalists, of course, you can measure very well the corresponding oscillation parameters. We run out of time, so I don't have time to discuss how you estimate the number of events in a more sophisticated way. But once again, I will put it in the Indico page of this school. So this is everything I wanted to say. I don't know if there's more questions. If not, thank you for your attention.
Thanks a lot, Ivan. It has been very nice from you. Also because just noticed that he's in the US and then it's night there. So thanks a lot for your availability and this lecture. We are running out the time. I'm gonna put the link for the visit just on the chat, so everybody can just click on the link and see the Zoom link for the visit, virtual visit to the Carl Frank laboratory. Just remember that next Monday we start with our matter at 10 a.m. And if you have any question, just write directly to Ivan. He can answer, or to Pilar in case you have some questions on the theory part.
Yeah, I think I am the only one, Esteban, in particle physics, so I am easy to find.
Very great. That's great. Stefan, I leave you with the last question that unfortunately maybe you can add it on your solutions. Is
Okay.
that why then when we speak about works, we don't speak about oscillations?
When we speak about?
Oscillations. We don't speak about oscillations in quarks, but about mixing.
There are oscillations in quarks. There are. I can make a comment in the talks, but there are processes that are looked for in collider experiments, for instance, in LHCb or in Bell or in B-factories, that are oscillations of mesons. So we do observe oscillations in quarks. They are harder to. So it's a completely different story because the typical oscillation distance is very small. Also, quarks come in mesons, so you have to observe the oscillations of these mesons. These mesons are short-lived. So it's kind of harder to do it. But in principle, in the sector, we also have oscillations.
Yeah, you can comment on your solutions then. Okay, thanks a lot again, and enjoy the visit, and see you on Monday. Have a nice weekend. Thanks again, Ivan.